Alright, problem number 11. A bank account is opened with an initial deposit of $5,000. So I know I've got like a starting value of 5 grand. The account earns interest at some rate and it is compounded monthly. So I know it is compounded 12 times per year. After 4 years of compoundings, so 4 years of compoundings, the account is worth $6,000. What yearly rate is the money being invested? So let's figure out how much money is made. It's compounded 12 times per year, and we are earning interest for 4 years. So that means 4 times 12 gives you 48. This has been compounded 48 times. Compounded 48 times. And remember that the number of compoundings is essentially what your exponent should be. So we've got the starting quantity of 5,000, and we are compounding that by multiplying it by some rate, and we're compounding it 48 times. And notice that that rate, since we're going to be increasing our money, that rate is going to be some positive decimal greater than 1, so 1 point something 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 right there is what we're looking for. So let's see if we can find it. So we know that this is going to equal 6,000. And so we can solve for r in this expression by taking 6,000, dividing it by 5,000. So we will get 6 over 5, because all those zeros cross off, and that will equal r to the 48. And this is going to be weird, but we're going to take the 48th root of both sides. And so we will get root 48 of 6 over 5 equals r, which is absolutely crazy. But crunch it. Think about what you could do. You could write this as 6 over 5 to the power of 1 over 48. It's probably how I'll do it on my calculator, but let's crunch that real quick and see what we get. So you do that, and you get 1.003805589, and I'm sure those decimals go on forever, but that's where your calculator stops reading them to you. But here's the deal. This is the r in our expression, but think about what our expression is telling us. Our expression is telling us that if you compound 48 times with this rate r, you get 6,000. But that's saying that this is then the rate per compounding, and we want the yearly rate. And how many compounds are there per year? Well, there are 12 per year. So if we multiply this number by 12, we should get our yearly rate. So we're going to take r times 12, and that will equal 12.046. And that will be my yearly rate. So this is 12.046%, just like that. And think about what we did earlier in the year, or earlier in the unit, I should say. Earlier in the unit, before we even talked about PERT, we came up with this equation: A of t equals our starting principal investment times 1. Whoa, that's not 1. Times 1 plus a rate divided by the number of compoundings per year, a yearly interest rate divided by the number of compoundings per year, to the power of our number of compoundings per year times t, our number of years. So if you think about it, that's essentially what we did right here. We had this equation. Our initial investment was 5,000 times 1, I did it again, 1 plus some rate, and it was secretly divided by 12. We didn't realize it at the time, to the power of n, the number of compoundings per year, which is 12, times the number of years, which was 4, and we got our exponent of 48, just like that. Now, they don't quite look the same at this point because then we simplified it a little bit. So we said that was equal to 6,000, just like that. And then what did we do? We divided by 5,000. So we got 6 over 5. Notice the same 6 over 5. Now at this point, that's equal to 1 plus r over 12 to the power of 48. And then what did we do? Well, we took the 48th root of both sides. And so we got 6 over 5 to the power of 1 over 48. And that was equal to, that was equal to this stuff over here, 1 plus r over 12. But we want to get r by itself, so I actually missed a step there. Before I multiplied by 12, I should have done a little magic trick. I should have gotten rid of that 1, so this should have just been a rate right there. The rate per compounding was that, because you can see here I need to subtract 1 from that. So I get 6 over 5 to the power of 1 over 48 minus 1 equals r over 12. And then I multiply by 12 on both sides to get my rate by itself. And if you go back through and take just this decimal version there and multiply it by 12, you should get this r right here, which is not going to be 12.046. That would be ludicrous. I should have realized that was too much. My bad. But let's take that decimal, 1.003805589. Let's subtract 1 from it to get just the decimal version of it. Let's multiply that by 12. And so using our previous approach, should have gotten 0.046 as that decimal. And notice the difference was I had that dude there. And if you crunch this the other way, type in 12, put a parenthesis, put another parenthesis, do 6 divided by 5, close one parenthesis, raise it to an exponent, do 1 divided by 48 as an exponent, should be in parentheses, subtract 1 from that, close your original parentheses, hit enter, and you indeed get the same value, 0.046, when we're rounding to 3 decimal places. So that was a fairly tricky problem, I'll give you that. But we're not even done yet. When will the investment be worth twice as much? So now that we have found our rate, we can figure out when the investment is worth twice as much. And so let's do that. But think about what we can do. We can use, I'm bibbling, babbling like a brook. I don't know. Let's write our expression. We want to know when it's worth twice as much. So we're starting with 5,000. So we're essentially saying 12,000. I can't do math. We're starting with 5,000. So we're going to get 10,000 equals this equation we wrote, which is our starting amount, 5,000, times 1 plus our rate, which we just found to be 0.046, but store it as a variable, divided by the number of compoundings, which is 12. All of that raised to the power of number of compoundings, 12, times some time t. But I don't want to go through and solve this by hand. You totally could. But again, kind of like the other calculator problems, I think your best bet here is probably to graph it. So graph the line 10,000, graph the line 5,000, parenthesis, 1 plus that value we just found, that rate, so I'm going to store that as a variable. So 5,000 times 1 plus that stored variable divided by 12, close it off, raise it to the power of 12 times x. And now we need to find that intersection point. But we need to find a good window. Notice the y value is up at 10,000. So I'm just going to make my y window from 9,000 to 10,000. No, 11,000. So I can see that there. What do we need for x values? Well, how long is it going to take to double? That's going to take a while. After 4 years, it went from 5,000 to 6,000, and we want to go to 10,000. So maybe for years, I don't know, I'll go 0 up to 20. Let's just try that and see if we can see it. I get my horizontal line, and then hopefully a graph is going to come through that I can see. Pooh, there it goes. When you graph it on that window, you get something that looks like this, really, is all it looks like on the screen, but that's okay because we can find that intersection point. So I can go second, calculate, intersect, enter, 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 and I get that it will take 15.207 years for my account to double in size. That's nuts. This was a hard problem. So just real quickly, going back to this bit that I goofed up there before, when you get 1.0038, yeah, that's your rate, but remember, it's got to be your rate plus 1, because if you want to increase something by a rate, you need to have that 1 there, because if you think about the distributive property, that 1 is like saying, hey, give me the quantity I'm starting with, and then also add this additional percentage on top of it. And those decimals are like the additional percentage. If you wanted to, when you're doing this, instead of doing all this algebra by hand, if you're able to write this equation right here, then you can graph it and calculate that intersection, and that would be another way you could find that rate if you don't feel comfortable with the algebra. But now that I'm here, I kind of want to solve this expression right here that we found by hand, just kind of to verify the work that we did. So I want to get that exponential bit by itself, so I'm going to get 10,000 divided by 5,000 is 2 equals 1 plus 0.046, that rate divided by 12, all that raised to the 12t. So I need to use logs to get that exponent down. So I'm going to take the log of both sides, so I'll get log of 2 equals the log of that whole thing, 1 plus 0.046 divided by 12 raised to the power of 12t. I'm going to plug it, so I'm going to get log of 2, boom, boom, equals 12t times, times the log of 1 plus 0.046, that rate divided by 12. So solve for t, so I'm going to get log of 2 divided by 12 log of 1 plus our rate, 0.046, something, divided by 12. And now crunch that into your calculator, and we should get the same value as before. So log of 2, close a parentheses, divided by, open a parenthesis, you have to have a parenthesis open here, 12 log of 1 plus our rate, which we stored, divided by 12, close off the parentheses, crunch it, and I get 15.207 years, which is exactly what we got right there. So that's good. I feel good about this now.